Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Problem 88. A closed reservoir contains oil of specific gravity 0.72. The oil surface is 2.75 meters above the center of the 75 millimeter diameter orifice with coefficients C sub V equals 0.95 and C sub C equals 0.65. If the horsepower available at the jet is zero point 0.8, determine the pressure in the airspace above the oil surface. If the orifice is on the plane of the reservoir that is inclined 60 degrees to the horizontal, compute the maximum range and the maximum diameter of the jet in millimeters. Neglect air resistance and observations are made when the flow is steady. So for the solution to help analyze the situation, let's have the figure. Then this is 60 degrees. Therefore, the initial angle that the jet uh, leaves the orifice is 30 degrees from the horizontal. So this is the depth, 2.75 meters to the oil surface. Then the oil surface is subjected to pressure P sub O. So this is R max. That's 30 degrees, and power in the jet is Q gamma O times energy in the jet. The only energy available at the jet is the velocity head, so that's VO square over 2G. So power in the jet is Q, specific weight of oil, times velocity head at the jet. Then, since Q is kaotog, C area O square root of 2GH, and C is equal to C sub C, C sub V. So Q equals C sub C, C sub V square root of area O square root of 2GH. Then VO equals V equals C sub V square root of 2GH, actual velocity of the jet at the vena contracta, square. So VO square over 2G, which is equal to C sub V square H in this case. So substitute into the formula or into here, power equals Q, which is C sub C, C sub V, area O square root of 2GH times specific weight of oil times velocity head, actual velocity head of the jet, which is C sub V square H. So combining, power in the jet is equal to C sub C, C sub V cube times area O times square root of 2G times head to the 3 hubs times specific weight of oil times head to the 3 hubs. So everything is given here. So let's substitute to solve for the head. 8 horsepower equals 0.65 times 0.95 cube, pi over 4.075 square, square root of 19.62, specific weight of oil 0.72 times 9.21 head to the 3 hubs divided by 0.746. The numerator is kilowatts, so we divide everything by 0.746 kilowatts per horsepower so that the unit will be consistent with the units of the left side, which is horsepower. So from here, we can solve for the head, and the head is 18.174 meters of oil. This 18.174 is equated to pressure head of oil in the airspace, which is P sub O over specific weight of oil plus this depth to the centroid of the orifice, 2.75. So 18.174 equals P sub O over 0.72 times 9.81 plus 2.750. From here, we can solve for PO, and PO is equal to 108.9 kilopascals. Then for the maximum range is equal to VO square sine 2 theta O over G from dynamics, or we can derive it supposedly, but just remember that R max is VO square sine of 2 theta O over G from dynamics. That's the horizontal range. So this distance here when the jet strikes at the same level as the level of the orifice. So VO is C sub V square root of 2GH 0.95 square root of 19.62 times the head 18.174. So V sub O is equal to 17.939 meters per second. We then substitute into this equation here. So R max equals 17.939 square sine of quantity 2 times 30 degrees over 9.81. So R max is equal to 28.41 meters. Then for the maximum diameter, it occurs at the highest point. So this is because the velocity at the highest point is the horizontal component of velocity, which is VO cosine of theta O, because the vertical component is 0 at the highest point. So therefore, the minimum velocity occurs at the highest point. Because the minimum velocity is at the highest point, then the diameter there is also maximum. Then by continuity equation, QO equals Q at the highest point, where QO is kaotog, and Q at the highest point is pi over 4 diameter of the jet at the highest point times velocity at the highest point. So 0.65, 0.95 area of orifice pi over 4, 0.075 square root of 2GH, 19.62 times head equals pi over 4 diameter of the jet at the highest point, square times velocity VO cosine of theta O, 17.939 cosine of 30 degrees. So from here, we can solve for diameter of the jet at the highest point, and that's the maximum 0.06498 meter, or in mm 64.98 mm. So that's it for this problem. Problem 89. Oil of specific gravity 0.85 flows in a horizontal Venturi meter with inlet diameter 200 mm and throat diameter 50 mm. Mercury is on the differential manometer with a deflection of 300 millimeters. If the head loss is 2 over 9 meter of oil, determine the actual flow rate in liters per second and the coefficient of discharge. So for the solution, let's have the formula which I derived in the lecture part on Venturi meter. So Q equals actual discharge equals pi over 4 diameter of the inlet square times diameter of the throat square root of 2g times quantity head small h minus head loss divided by diameter of the inlet to the fourth minus diameter of the throat to the fourth. So this is the configuration of this problem to help us analyze the situation. Although the formula is pi over 4 diameter 1 square diameter 2 square root of 2g quantity h minus head loss over diameter 1 to the fourth minus diameter 2 to the fourth, where h is the difference in pressure head and elevation head at 1 minus at the inlet minus or it is P sub 1 over specific weight of the flowing fluid plus elevation head at 1 minus quantity pressure head at 2 P2 over specific weight of flowing fluid plus the elevation head at 2. So H is P sub 1 over gamma of flowing fluid plus G sub 1 minus P sub 2 over gamma plus G sub 2. So Z1 and Z2 are zeros in this case. So even if the orientation is inclined or vertical, there's no problem with H here because this is the expression for H, and whatever is the derived expression for H here, that will be also applicable for any orientation of the Venturi meter, whether it is inclined, horizontal, or the flow direction is vertically upward. No problem. So let's derive this expression, although in this case Z1 and Z2 are all zeros. So even if Z1 is 0 and Z2 is not 0, the formula that we can derive for H in terms of the specific weight and the deflection of this manometer liquid will be the same. So H is P sub 1 over gamma of oil minus P sub 2 over gamma of oil in this case, because Z1 and Z2 are all zeros if the datum is through 1 and 2. So even if the datum is anywhere, Z1 minus Z2 would still be 0. So we then sum up pressure from point 1 to point 2 along this tube. So P sub 1 plus specific weight of oil, flowing fluid, times quantity Y plus Z. So that's the present or current pressure here. So the pressure here is equal to the pressure here by principle at the same level on a homogeneous fluid at rest. Then we rise, so minus specific weight of mercury manometric liquid times Z, then minus gamma specific weight of oil times Y equals P sub 2. So take note that we have gamma OY here, then minus gamma OY, so it will cancel. So if we transpose to the right, the terms here except P1 and P2 should also be transposed to the left. Then we'll have gamma of HCZ minus gamma of oil Z. So if you factor out Z, the right side would be gamma of mercury minus gamma of oil times quantity Z. So P sub 1 minus P sub 2 equals gamma of mercury minus gamma of oil times Z. Dividing everything by specific weight of oil, so we have P sub 1 over specific weight of oil minus P sub 2 over specific weight of oil equals quantity specific weight of mercury over specific weight of oil minus 1 times Z. So take note that specific weight of mercury is specific gravity of mercury times specific weight of water, while specific weight of oil is specific gravity of oil times specific weight of water. So we have specific gravity of mercury times specific weight of water over specific weight of oil, specific weight of water. Cancel gamma of water minus 1 times Z. So therefore, H, which is difference in pressure heads between 1 and 2, it is reduced to this expression here, although this is the general expression. Then it is equal to specific gravity of mercury over specific gravity of oil minus 1 quantity times Z. So take note that H is equal to this, the right side, for even if H original is in this situation here, this will still be the value of H. This is still the value of H. If we write energy, if we sum up pressure from point 1 to point 2. Even if the orientation is inclined or vertical, this will still be the general formula for H. So we may generalize it as specific gravity of the manometer liquid over specific gravity of the flowing liquid or fluid, then minus 1 times Z. So H is 13.6 over 0.85 minus 1 times 0.3. So H is equal to 4.5 meters of oil. So having found H, 4.5 meters of oil, then we substitute it here. The head loss is 2 over 9. So Q is pi over 4 times 0.2 square times 0.05 square times square root of quantity 2 times 9.81 times quantity 4.5 minus 2 over 9 over 0.2 to the fourth minus 0.05 to the fourth. And times 1000 to convert it to liters per second. So Q is equal to 18.02 liters per second. Then the coefficient of discharge is square root of, or coefficient of discharge is the ratio of actual to theoretical discharge, and it is also square root of H minus head loss over H. So C, which is Q over Q sub D, is also square root of quantity H minus head loss over H. So we have already found H, 4.5, and head loss is 2 over 9. So we then substitute and apply this into this equation, into this formula. So C is equal to 0.9750.